our resident astronomer, Bill Stent, the telescope gent. He's going to give us a bit of a what's up in the sky for Feb. So without further ado, I now give you Bruno.
The lack of mic seems to be coinciding with the frog that I swallowed, so I'm going to be doing this a lot. Thank you for the introduction, Mark. And good evening, everyone. How many people have heard of Whitehall? Educated audience, thank you. Well, wonderful. Well, I can sit down now. Tonight we're going to talk about how a cloud of gas, mainly hydrogen, some helium, converts into a black hole and eventually into a white hole in some stages in between. So let's start with that. But first, a little review of the Big Bang. At the left-hand side, you can see a big yellow blob there. It's a great misnomer because the Big Bang happened in total silence, an infinitesimal little foot, and nothing like that at all. This is just children's fantasy. It is based on standard model of cosmology. There are many different models, so I'm going to follow that. So if you have a different idea, it's because you may be subscribing to different models. So the standard model of cosmology says that in primeval vacuum, prior to the birth of our universe, there was a fluctuation, a quantum fluctuation in the vacuum. And that imbued the local surrounding area with energy, and it expanded outwards at the speed of light like a bubble, and that eventually expanded slowly at first and then very fast in an exponential manner, as you can see, which is known as hyperinflation. And then the energy has cooled because the universe expanded, the density of the energy lessened, and as a result of that, the energy of the inflation, which is known as inflaton by coincidence, has been distributed a bit more. So by now, the universe is about the size of an orange. It's made entirely of photons banging into each other at microscopic distances. Now, as it expanded even more, then the quantum fluctuations which were there were already imprinted upon its behavior. And today's patterns of galaxy formations are thought to be based on that. I should mention that the whole business of how the galaxies have formed is still under intense study. There is no standard theory. There are many different versions of it, and none agree with one another. So here we have the hyperinflation, and the energy, the inflaton energy, is now coalescing into what is known as massless particle, also known as a quark-lepton soup. Quarks are fundamental particles, and leptons as well, from which you and I are made, and everything that you see around us. So we now have a lot of massless particles, and then the vacuum of the universe goes through three sequential phase changes. First, the strong nuclear force field departs, Higgs field comes into existence, then electroweak nuclear force separates, and it is at that point where electromagnetic fields and weak nuclear force fields separate. That's when particles acquire mass. At the same time, prior to that, dark energy is created. There's a lot of controversy what it is and how it's created. and the universe created equal amount of matter and antimatter. Antimatter is simply matter with an opposite electric charge. So an electron, antimatter of electron is known as a positron, for example. Now, antimatter and matter annihilate each other, and 1 in a billion in favor of matter survive. This is what the universe is made of now. Not a very economic ways of making universes, would you agree? So that's where we are right there. Eventually, quarks bind into a nuclei by new fourth particle known as gluon. Gluon because it glues the quarks together and it keeps them within the perimeter of the nuclei itself. In fact, the strength of the gluon defines the perimeter of the nuclei. I've heard a talk by one of the physicists that a lady whose ambition was to measure the size of a nuclei, and I thought, half luck, lady, because it keeps vibrating all the time. It's bigger, smaller in every direction. So it's a continuing story. Okay, so now we have nuclei of hydrogen, which is essentially a proton, and when two protons collide by the media of weak nuclear force, I won't go into the physics of it at this stage, one of the protons gets transformed into a neutron. And now we have one proton and one neutron. Together they stick together and they make what is known as deuterium or deuterium. The naming convention is deuteron, triton, hydrogen, or deuterium, tritium, and so on. Two different schools of thought. So we have a nuclei, and for 380,000 years, they simply exist as ions. Ion is an atom without electrons. So there's a lot of terminology in this, and I hope you're following all that. So a nuclei is an ion in general. In this particular case, it happens to be an ion of hydrogen atom, which is not yet an atom, and it is in a form of a proton or a neutron. Okay, so we got that far. If you're not confused yet, then you're doing well. 380,000 years has passed now since the Big Bang, and at that time, protons are capable of attracting an electron. So once they do that, we have chemistry. We have gas, proper hydrogen and helium gas. The universe has created 75% of hydrogen, roughly about 25% of helium, and a smidgen of lithium with an absolutely tiniest amount of beryllium. It's hard to measure it. So now we have clouds of hydrogen floating, and when I say clouds, I mean 100 times larger than our galaxy. We're talking about humongous clouds. And within those clouds, which are surrounded by dark matter, gravity of the cloud itself is compressing the cloud towards different centers. I'll show you on the next slide. This is, by the way, a picture taken from a screen of a computer simulation of what actually happens. You can see where the filaments are denser. It's like rivulets of water. They form together downhill, and they form a stream and then a river. In the same way, where there is matter attracts more matter by sheer act of gravity, and so rich areas get richer and poor get to have voids. So in the areas where the matter has gathered more consistently and in greater density, this is the area where the first stars would have formed. Now, a cloud is usually stationary, but because of the different densities throughout, it eventually acquires a momentum and it starts rotating. Once a cloud of gas starts rotating, it flattens because it starts radiating electromagnetic energy. It flattens and it concentrates in the center. And, and gravity squeezes it more and more and more until such time that the gas gets very, very hot. So we come to the next stage of a protostar. I won't read what's on the screen. I take it you are fast readers. So on the right-hand side, we have, sorry, on the left-hand side, we have a picture of a protostar. Notice that as soon as a protostar acquires a temperature of about 10 million Kelvin degrees, it blows away the rest of the gas away from itself. From then on, the star will never get any bigger. And the gravity keeps squeezing it even more, because at this point, the thermonuclear reactions are too weak to resist the push of the gravity inwards. What do I mean by thermonuclear reactions? Thermal means heat, nuclear means nuclei banging in together and sticking together. So if you have two protons traveling in the same direction, they will stick together under that pressure and form a neutron. And then a proton and a neutron becomes a deuterium. And this is as far as the proton star goes, no further. Dimmer stars, such as brown dwarfs and red dwarfs, also go only up to the first level of the thermonuclear reactions. Our sun is a bigger star again, so it can convert hydrogen to helium and some heavier gases, neon and oxygen and so on. So on the right-hand side, we have a picture of a large star, and you can see the black arrows pointing inwards. That's gravity, trying to contract. The gases themselves have gravity, and they contract themselves towards the center. The center is shown in white, where the thermonuclear reactions occur, and in red, going outwards, is both heat and radioactivity in form of X-rays, gamma rays, visual light, visible light, and UV and whatnot, microwave, and so on. So now we have a protostar contracting, and once it contracts to the point where it heats up even more, it reaches about 14 to 15 million degrees Kelvin, and from then on, it is a proper star. A star is born, like our sun. Okay. Now, this is a somewhat complicated picture of the life of a star. At the right-hand upper corner, you see red arrows of gravity pushing all the gases towards the center, trying to contract the star. And in purple or violet and green, you have both radioactivity and heat, matching the gravity force. So everything works well, and then the fuel at the center gets used up a little bit. So gravity says, hello, I got you now, and it squeezes the gases even more, and by doing so, it increases the temperature within the center of the star. The core of it heats up a bit more and recovers the rate of production of thermonuclear reactions. What I mean by that is conversion of hydrogen into helium. That supplies about 90% of the energy that star has. Now, eventually, second from the left diagram, eventually all the fuel, or most of it, in the core runs out. And when that happens, things happen very, very fast. Now, gravity starts to force everything towards the center. and it squeezes the core of the star smaller and smaller and smaller until it reaches a critical radius known as a Schwarzschild radius, where a black hole forms. It may be that a neutron star forms first, but here we're talking about production of black holes, so I will stay on that track. So at that point, an event horizon forms around the black hole, and a black hole, due to its physics, is unable to accept all that gas that is trying to force its way into the black hole. It belches. And what happens then is that, like when the bus is full, now more people can get on the bus. So there's enormous pressure at the event horizon of the black hole, and the temperature now reaches about 100 billion degrees. It is at that point where there's preponderance of thermonuclear reactions and production of neutrons and so on. And this is where all the heavy elements are made, gold, platinum, and so on. So the ring that you're wearing on your finger was most likely made during the death of a star. Now, there are other ways to do it as well. So now the third picture from the left shows the core has now collapsed, and now more collapsing can happen. So the pressure is enormous there, and the process reverses. We have a shock wave building outwards. The red ring signifies such a shock wave. Of course, the next diagram to the right shows that the shock wave travels outwards, and it meets enormous amount of pressure from the gas coming from the outside, and it stalls for a moment. Eventually, the shock wave wins, takes over, and when it reaches the perimeter of the initial size, the diameter of the original star, it blows away all the gas into a nebula which travels at enormous speeds. You probably have photographed such nebulas yourselves. So this is how a star ends its life. And the common wisdom was that once it reaches the state of a black hole, then wow, that's it. That's the end of it. The black hole just devours more gas and lives for billions of years, and Bob's your uncle. Well, apparently not. So let me tell you a little bit about black holes before we move on. I'll try to get rid of the frog. On the left upper diagram, we have a two-dimensional image of a heavy ball resting on top of a trampoline. This is how popular literature describes how mass distorts space-time. Now, space-time is nothing else but gravitational field. So it's kind of describing butter in terms of butter, because the mass of the black hole creates the gravitational field, and it itself is curved. That's one way of looking at it. The other way of looking at it is that the mass of the black hole disturbs the space-time, and that's why this is curved. Do you see what I mean? Different points of view. In fact, the entire concept of relativity is based on observer. What one observer sees is not what another observer sees and experiences. If you are in two different rockets heading towards each other in space, you might say, well, how fast are you traveling? And the other guy says, with respect to what? With respect to me. Well, he says, I'm stationary, you are the one that's traveling. And the guy that asked the question says, no, I am traveling and you are stationary. So it's all relative. And the same thing happens when an observer from a rocket outside of a black hole is looking at an astronaut who decided to jump into a black hole. He will see, just assume an ideal black hole. There's no accretion disk, there's no great temperature around it, there's no violence, nothing. Just a neat little black hole sitting by itself, saying hello. So an astronaut jumps in, and at first he goes very fast, towards it and then slows down. This is what an observer outside sees. And eventually the astronaut stops. He doesn't actually stop. This is what the observer thinks, that it stops, it becomes a little redder, and then just disappears. But the astronaut, nothing like it. He just goes straight through the event horizon, and for him, time goes on as it always had, and suddenly he starts feeling something funny with his legs. They're getting elongated, and the rest of his body getting spaghettified. Eventually, he reaches the point of singularity, and that's the end of him. So this is critical, that we describe things in terms of which observer are we looking at the issue from. So looking at the geometry of a black hole, this geometry is according to quantum mechanics, also known as quantum physics. It's called quantum mechanics for historical reasons. When in 1920s, scientists such as Heisenberg and Schrödinger and people like that, when they worked on the quantum physics concept, they expressed everything in terms of matrices. How many are familiar with matrices? Raise your hand. Mathematical notation? No? Rows and vectors and so on. Every point on a curve, if you have a curve like that, then every point on a curve is described by something called tensor. Now, tensor measures the tension, the pressure that is required to keep up that curvature. And that tension is described by 16 different equations within the Einsteinian relativity. And they expressed it in terms of matrices. So it used to be known in the first place as wave mechanics, and then it was shortened down to quantum mechanics, hence quantum mechanics. But quantum mechanics and quantum physics are the same thing. Physicists generally talk in terms of quantum mechanics. Okay, so quantum mechanics says that a black hole, looking at it from the outside, has an ergosphere shown in purple. This is the area where when a new star approaches, or any gas cloud approaches the black hole, that's where it is first attracted. It goes around in a almost flat plate around the black hole, and eventually particles of gas collide with each other and change direction, and they fall in. Black holes do not suck. Okay? Take that as a given. I've been there, done that. Experience no suck. Okay. Now, so ergosphere, ergo in ancient Greek means work. This is where work is being done. And this is a rotating black hole. You can see at the top the axis of rotation. And physicists talk about frame dragging. Frames of space-time are being dragged by the magnetic fields and the gravitational field excuse me, of the black hole. So that's ergosphere. Then you have the outer horizon, outer event horizon in yellow. Once you go through that, there is no coming back. The curvature inside, once you get in, it's like being inside a basketball. You try to get out, but the gravitational force fields curve. So you have to follow the geodesics. You can't just go straight. It's not, you will hear and read in popular literature that even light cannot escape. Light doesn't want to escape. Light just goes straight in. But even if it did want to escape, it wouldn't be that it hasn't got enough strength to get out. It is more because it follows the curvature of the gravitational field within. That's why it can't escape. It just keeps going round and round. Okay. The greenish, bluish kind of inner horizon is where time and I nearly said it, I shouldn't say that. Let me rephrase that. The space and time coordinates change. It's not that spatial dimension becomes a time dimension. It's simply a mathematical coordinates that change within that. So when you are inside the black hole, you don't ask where is the singularity, rather when, because of that convention. You follow me? Okay. Time just ticks on as it always had been before. And then Einsteinian general relativity says that singularity, where all matter and energy is concentrated in an infinitesimally small volume with almost infinite amount of energy, that obviously is nonsense. Einstein understood that very well. But that's what his mathematics were showing. He used converging series, mathematical series, which eventually come to a point. And the same happens with the Big Bang. Black hole is very much like a Big Bang, looking in reverse. So obviously that doesn't work. So modern physicists, according to quantum mechanics, think that the singularity is actually a ring of indeterminate shape and indeterminate volume and region. It keeps vibrating like that all the time. Okay. Once the black hole stops eating, it starts radiating heat and Hawking radiation and information. Information is not lost. I won't go into that because that's another 1.5 lecture on that. I just wanted to mention that. Okay, so that's the black hole. There are 3 classifications of black holes, only according to size. Very small black holes, of which there's a preponderance, millions of them. And then there's a shortage of medium-sized black holes. And then they are the behemoth, very large black holes which have billions of solar masses. So the 3 largest that are known is one with the number at the top. And it has a mass of 40 billion suns. Now, you can see the sun, the dot in the center, and the yellow ellipse around it. That's the orbit of Pluto. So the diameter of that black hole is 37 times larger than the orbit of Pluto. If you fell into such a black hole, you wouldn't even know. It's like falling into a cloud. The density would be very low, but then gradually you would start being spaghettified. This one has been measured and is well known. The next is a TON 618, estimated at 66 billion. And I think there is one that is 100 billion, but it's so far that the error starts increasing. If you draw a graph like that, in terms of distance versus accuracy, then from the graph, the error bars get bigger and bigger. So it's not quite certain how heavy it is. Okay. I hope you're thinking up of some good questions, because now we come up to some difficult stuff. This diagram shows a departure from Einsteinian relativity. And you can see the star at the top. Once the core collapses, all the stuff that was within the core is supposed to go to singularity. Well, obviously that is not true, and no one believes it anymore. However, string theorists, for all the bad publicity that they have received over the past few years, they've come up with some very useful tools which are used in both in relativity and in quantum mechanics. And several string theorists have come together, and they worked out that the core of the star keeps on collapsing. In other words, the black hole doesn't stay like that the way it is. The core of the original star keeps on collapsing, becomes smaller and smaller, and the volume of the star is like a trumpet with a big mouth at one end and narrowing and narrowing. And the next, and eventually it finishes up to be a white hole. I'll talk about that in a moment. So let me show you a bit of introductory diagram. The first guy to think of a white hole was a Russian physicist, Igor Novikov. And they think that they've discovered an evidence of something called gamma ray burst. When a star collapses, it gives off momentous amount of radiation, gamma radiation. Gamma radiations are of very short wavelength, highly energetic, and they melt everything in their way. But they are traveling waves. Whereas this one, discovered and shown here, didn't go anywhere. It just stayed there, which suggests that the object is stationary. And I think it may just be a white hole. I'll define what I mean by that. Now, at the top of the diagram, you see an ordinary black hole, as it was photographed by several different telescopes around the world, and then all the information was put together over several months, and that's the image that they've produced. Now, the reason why you are seeing that curve at the top is because of gravitational lensing. Einstein proved in 1915, or rather postulated in 1915, that light passing over a star or any mass, black hole or planet, will bend a little bit. And Eddington went to one of the islands and was lucky enough to photograph the proof. From then on, of course, Einstein became a rock star and famous and so on. So this is what you see. You see the back of the accretion disk, which is around the black hole, as if though it was on top of it because of the gravitational lensing. The gravity field of the black hole bends the space-time in such a way that the light appears to be coming from behind towards you. That's why it looks like that. And the diagram at the bottom left has three elements, one of which, of course, is the gamma ray burst, and the other one is a transition of space-time itself. When I say space-time, you need to think of quantum state of the vacuum. Okay, it isn't static. It compresses, and when it compresses to the point where it cannot be compressed anymore, it reaches what's known as a Planck level, the ultimate smallest possible volume, 10 to the minus 99 of a centimeter cubed. At that point, the space-time itself, the field, goes through a phase change. Now, don't ask me what it is, because nobody understands it, but it happens everywhere. In your phones every day, in any electronic device, you have jumps, you have quantum tunneling, and all of that. This happens in every star on a daily basis as well. So quantum tunneling and space-time quantum jumps occur all the time. I'll give you another example. In your high school, you would have learned that a nucleus of an atom was in the center, and in neat little circles, orbits of electrons. The further away, the more energetic. And the ground level was the one that was closest to the nucleus. Nothing is further from the truth. They don't travel in neat little circles, not even ellipsoids. They exist in weird. Have you ever had a children's party and it makes little crocodiles or elephants out of balloons? This is sort of what they look like. I'll have to show you a picture of what they look like. So what happens here is that the blue line represents the jump, the quantum state rather the time or the space-time in which a phase change occurs to quantum state of the space-time itself. Nobody knows how this happens in any of the media I've just described. But an analogy in a classic world would be like this. If I throw a ball, a tennis ball, at a wall with some force, I expect that it'll bounce back. Not so with a quantum particle. The quantum particle flattens out and its magnetic field stretches out and goes past the wall and reconstitutes itself on the other side. This is quantum tunneling. Weird, isn't it? But that's normal. And it happens in every electronic device that you have. Okay, so now we think that the quantum star that had been compressed to the Planck level makes that quantum jump and re-emerges on the other side as a white hole. Wow. Apparently, the mathematics of that are faultless. Of course, this sort of thing can't be proven because no technology exists today for this to happen. But in the same way that many things 100 years ago were considered to be fairy tale, today they're every day. Black holes are normal now, so why not white holes? I'm nearly finished. Okay, so let me tell you a little bit about loop quantum gravity, upon which all this is based. You may remember from the old movies, in 12th century, warriors used to wear mesh sort of shirts to protect them from arrows, and they were made of rings connected together. According to Rovelli and Lee Smolin and several others, you know, the leaders in this loop quantum gravity, space is made up of these little energetic loops which vibrate. Where they are is impossible to tell because everything in quantum mechanics is based on probabilities. You cannot for certain say anything at all. Where is a particle at any one time? How fast is it traveling? If it's completely stationary, you can tell where it is. But as soon as it starts moving, you cannot for certain say how fast it's moving. You can only assign levels of probabilities. In the same way, loop quantum gravity works. So these areas here in green, they represent space. Sometimes they draw them just as dots. And the lines in between them are the gravity force that holds them together, okay? Quantum mechanics regards gravity as a force, whereas Einsteinian relativity did not regard it as a force. Let me describe that graphically. Imagine that you placed a very heavy artillery ball on a slack trampoline. It'll curve. Every planet, every mass, black hole, star creates such a well, and if you place something on that well, it'll tend to go to the lowest energy level, fall down. This is why if I step off here, I will fall down because I'm falling down that gradient. There is no force attracting me. I'm just falling down that gradient. I've heard counter arguments to that. I said, yeah, Bruno, you say that gravity is not a force. Drop a brick on your toe and see what you think of that. Okay. All right. So that's Rovelli over there. And this was his loop quantum gravity based on string theory. So this is what happens here. The star the core of the star has collapsed and shrunk, and the volume thinned out until it reaches a Planck level, then goes through a phase change, tunnels through that area and comes back and grows with negative gravity, this time repulsive gravity, and becomes a white hole. You cannot enter into a white hole. You can enter into a black hole, but you can't come out. But you can come out of a white hole, but you cannot enter it. It's exactly the opposite. Now, all this was predicted by general relativity, which Einstein published in 1915. He didn't really understand the consequence of that. That came later. But there's more. But first, let me describe the two different approaches. Rovelli says time travels upwards along that arrow on the left, and there's the original star. It collapsed. It keeps collapsing more in the middle, and when it gets to the critical level, it jumps, reverses, and goes back, and comes out the same way. This is Rovellian's small inversion. Other scientists think something different happens. They followed Einstein's ideas, where yes, the star collapses in size, the core becomes smaller and smaller and smaller, and then it goes through the physics of the loop quantum gravity in the center, and then something different happens. Now, Einstein already knew and understood that. Einstein and Rosen came up with an idea that that jump is made via something called Einstein-Rosen bridge. They called it that. A bridge forms between what was the quantum state of a black hole and not quite yet a quantum state of the white hole. Today we call it a wormhole, an energy tunnel through which space-time tunnels through. These words probably don't mean anything to you much, but because they are physical terms. And then an opposite of what went in comes out. So you can see that this white hole is an antidote. It doesn't come back the same way, it comes back the opposite way. Now, there are some interesting consequences out of that. The bottom diagram on the left is the Einstein-Rosen bridge. And another fellow joined them by name of Podolsky, and he said that something strange happens between them. In order that that bridge actually forms, the two must be entangled. When two quantum particles crash into each other, they are immediately entangled together. What does that mean, entangled? It means that they are part of the same system. And no matter how far apart they are, they will be entangled. So much so that when you make a change to one of them, the other one immediately changes as well. Weird, isn't it? Einstein called that spooky action at a distance. He couldn't accept it. To the end of his life, he could not accept that. He says reality is not like that. The moon is there whether I look at it or not. That's called objectivism. There's another famous, how am I doing for time? Yeah, shut me down if you want to. Yeah, okay. Imagine that a quantum particle, such as an electron. Now let me define what I mean by quantum particle. A quantum particle is a vibration in its native field. That means that an electron is a vibration in an electromagnetic field. It is not a thing in itself. It's just a vibration in the field. Let me see if I can illustrate it a little better. Say you are standing on the edge of a pond and you have a long stick, and you bang the water gently, the surface, and you notice that it makes waves. And those waves propagate in circular fashion outside, away from the source. This is why people say that photons are waves, that we have wave mechanics, that particles are waves. Now, for energy reasons, they study particles as golf balls because it's easier. Some people prefer to talk in terms of waves. But a particle is neither a wave nor a golf ball. So once you accept the fact that it's just a vibration in the field, then when two vibrations happen, they are in the same field. They're part of the same system. So it doesn't matter how far apart they still stay the same system. And they are entangled. So when two black holes get entangled and a bridge, a wormhole forms between them, they are entangled. That has tremendous philosophical implications. It means that you can travel in time. Wouldn't that be nice? If Einstein, as a young man, could jump into a wormhole, visit himself when he's older, see a paper on relativity and say, I find that interesting. Come back and publish it. But there's a nicer example. In the diagram on the right, you have a black hole in blue and a white hole in purple. Now, Bob is in love with Alice, and they live in different galaxies. So he jumps into a black hole next to him, which is entangled with a white hole in another galaxy where Alice lives. He jumps in there, gets spat out by the white hole, and Bob's your uncle. They're happy forever after. Nothing like that is possible. They would be converted into quantum particles long before. Now, I don't have a piece of paper, but I can illustrate it this way. Say that we have a flat sheet like that, okay? Or relatively flat. And there's one black hole and there's another. Now, we don't have the technology to do this, but if it was at all possible to bend space-time like that, now the black holes are very close together, and the wormhole is in between them. So all you need now is a capability of bending the gravitational field so much that it appears to entangle the two. In principle, it's possible. Mathematically, it's possible. And that's shown in the picture at the top left. And we got it down pat? No worries. Okay, good. Okay. While I summarize, we can think up of some devilish questions. So we talked about primordial gas clouds, which collapse into galaxies. Oh yeah, one thing I did forget to mention, that astronomers and astrophysicists think that if a cloud does not rotate, then it's quite possible that that primordial cloud has shrunk and then accelerated and went straight into a black hole, bypassing the stellar process altogether. So this is the primordial black hole. And some people think that perhaps the very large black holes were created that way because there wasn't enough time in the life of the universe for them to eat up and merge with others and eat up enough gas to get so fat. So that was one idea. So the first galaxies and protostars formed in filaments of gas around 100 million years after the Big Bang. Now here comes a surprise. James Webb discovered that 30 million years after the Big Bang, there were already galaxies. Wow. That means we need to rewrite the whole chapter of the early stages altogether. And then the first stars were also known as the early blue giants. They were made mainly of hydrogen. They burned very, very fast because of the huge pressure, the huge gravity. And you might say, well, how is it that a very large star burns its fuel faster than a small star? Because it has so much gravity, so much pressure, the temperature is so high that it eats itself from the inside very, very fast. They live for about 10 million years, whereas our sun has an expectation of 10 billion. We're about halfway through. So Yes, so they lived short life and they contracted to a black hole. The possibility of a white hole was first predicted in 1964 by Novikov and potentially detected recently. The core of the original star shrinks and forms a black hole, which keeps on shrinking in an elongated volume, bounces back from a white hole with a repulsive gravity. As a result of that, a tunnel forms in between the two, and after the transition between black and white hole, facilitating time travel. Now, if you did jump into a black hole and came out of a white hole, you would come out billions of years ahead of time. So that's not much good to you. Nobody would speak your language. And on that note, I'll quit. Thank you very much.
Just got to put my phones down because I've got YouTube open and Facebook. And are there any questions from the audience? There are. I'll come to you in a minute while the others think of some questions, because there's a few questions here. The first one is, Bruno, what is your theory in relation to the formation of globular clusters? Is there merit in them being stripped galaxies? I've been unable to find a definitive strong theory as yet. However, unsure if this is an area of your expertise.
Well, actually, this is not my area of expertise, and there are no experts on that topic. You may recall that earlier on I said that there is no definitive theories of how galaxies actually formed. But the standard model says that small galaxies joined and became bigger, and they formed clusters, and then they formed systems and so on. I actually have a map, which I didn't bring with me, of the sky, which shows the 18 major structures. They are known such as the Great Attractor, the Sloan Wall, the Hercules, and so on. There's about 16 of them, and they all move around and merge with one another. But there's no specific theory that has been both mathematically consistent or experimentally proven of how actually galaxies form.
Hopefully that's answered the question. One down, two more to go, and then I'll come out to the audience. I think you actually answered this one. Are black holes wormholes? Can we go into a black hole and come out somewhere else in the universe? Which you did answer, didn't you? So
I should comment that we are always talking about idealized systems. When mathematicians and physicists want to calculate something, they focus on one particular thing and ignore everything else. This is known as the round cow approach, and it comes from an anecdote that a farmer had a problem with his cows. They weren't producing enough milk in comparison to other farmers in the district. So instead of sending him an agricultural expert, they send him a physicist. And the first thing he said to the farmer, he says, let's assume a circular cow, which ignores all other respects. Sorry, what is the question? I forgot.
Oh, you answered it already, but it was to do with black holes, wormholes, which I think you gave.
Yeah.
And the last one is, I thought information loss does occur in black holes, and this is Hawking radiation. Doesn't this radiation mean that pure information is lost, which leads to entropy?
I spent myself and my mates spent at least 2 years of concentrated research and study on the subject, and you need to appreciate that even though I licked a little bit of mathematics, most of it is at such a level that I just keep banging my head against the glass ceiling, and that's the language in which it is all described. However, the common consensus is that information is not lost in black holes. If you like, I'll come back and describe how that happens in another talk, because it will take that long. But essentially, it goes like this. Information is stored on the surface of the black hole, which is just an energetic surface, just like a layer of magnetic field, and tiny little magnetic fields, isolated magnetic fields, make up what we call ones and zeros. I know it's a kind of esoteric and idealized fat cow type of approach, but it's a way of representing it. So information is stored on the surface of the black hole. And as the black hole evaporates, some of that evaporates as well, and none of it is left in the center. Another version of it says that the information of particles, I should explain what I mean by information. We're talking about quantum particles here. So quantum particles have spin, they have energy or mass, which is the same thing, and they have electric charge. They are the only bits of information that any quantum particle carries. So once an electron falls into a black hole, that information has fallen into a black hole. Now, there are a number of scientists which have just recently, 2016 and 2022, they proposed an idea where little islands of this information forms within the black hole, which is within the volume of the black hole, but not of the black hole. They are entangled with the bits outside. And so they form little wormholes through which they escape and go off. Now, I know it sounds a bit like a fairy tale, but most of these theories do a little bit. So the general consensus is that information is not lost. Hawking has proposed that it is via Hawking radiation, which is purely thermal, and he made a bet with John Preskill, and the popular rags will say that he lost an annual subscription to Penthouse, and another lot says that he actually lost a subscription to Encyclopedia of Baseball or something like that. But in the end, he accepted the fact that no information is lost. It's one of the cornerstones of quantum mechanics that some entities must be conserved. Energy is conserved, electric charge is conserved, and information is conserved. Mass is not conserved. There are many other things that are not, but information is.
We've got a question from the crowd, and then we'll get Mr. Telescope Gent to get up and give us a tour.
Tell me if my thinking's wrong here, but I thought to keep a wormhole open, you needed negative energy. Just wondering if there's been any movement in getting over that little difficulty.
The concept of positive, negative depends on the viewpoint. If you are inside of a black hole, then you view everything with negative energy. If you are on the outside, everything is positive energy. Let me explain it to you this way. Say you are in a church and there's this humongous pendulum or a chandelier, and someone gets it in motion. When the chandelier gets to its utmost level that it can go, it has lost all its kinetic energy, but it has lots of potential energy. And if there was no friction and if it was a circular cow situation, then it would keep on going like that forever, perpetual motion. So energy cannot be lost in closed systems. In open systems, yes. It simply changes from potential energy and gets lost via friction, heat, and interaction and so on into kinetic. So you could argue that the energy that is pushing the chandelier out is positive energy. And when it's coming back, it's negative energy. You see what I mean? It's just a matter of convention. It's a viewpoint. There's no such thing as negative energy. Energy is always positive. But from which coordinates you look at it, It's either positive or negative. There are also other interpretations of that, and I'll just mention one quickly. In vacuum, in the fields, they vibrate. And as they vibrate, when they're excited, they emit virtual particles, usually positive and negatively charged. Now we're talking about electric charge, not negative energy. However, when we're talking about photons, photons are its own antimatter, its own antiparticle. So there's a photon and antiphoton. And when the photon is created in space, in the vacuum of space, very close to the event horizon of a black hole, the strength of that gravitational pressure actually splits the photon into photon, antiphoton, and reverses one of the phase. So one photon is going like this, the other one's going this way. The one that's going down is known as negative energy. It's just a naming convention, okay? And apparently, because that's based on its spin. This phase change is you know that particles have a concept of spin. Does anyone understand what quantum spin is? Because if you do, please explain it to me. It's just an intrinsic property of a quantum particle, which has absolutely nothing to do with the spinning top. But the best analogy I can give is that if you have a wheel with wooden spokes driven by an electric motor, and you come with an iron bar, shove it in between the spokes, you will stop it. The wheel still wants to rotate. It has magnetic moment. That's what spin is, okay? This energy that wants to spin. And particles, quarks, have either plus half or minus half, meaning up or down, which once again is convention. There's no up or down. So the photon that is going down has a spin opposite to the one that has gone up. And in doing so, it interferes with the energy and particles which are inside, which has a positive spin. So they annihilate each other and they reduce the mass of the black hole. This is skipping on stones, headlines only type of children's explanation.
Thank you, Bruno. Do we have any other questions? I think what we might have to do is get you back into a sit-down chat where we can just, instead of having just a topic, just ask a series of questions that you can answer, a discussion. We'll get you back in a few months' time. We'll do that. But Bruno, thank you very much for your talk. It was wonderful. Much appreciated. And yeah, we'll have you back in a few months' time.
Okay.
Thank you. Now it's time for Mr. Bill Stent, the telescope gent. And while he sets up, I just wanted to sort of give everyone an update. We do have, as I said earlier, tickets available for the Messier Star Party. They're online now. You can go and book them. We have, I think, if anyone's going to Falls Creek this weekend, we've got some volunteers heading up to Falls Creek to do a tour of the night sky up there. We've got an ASV, Mornington Peninsula and Latrobe Valley Astro Group weekend, where there's still tickets for members to come down to Buchan, down in Gippsland to hang out. And the Melbourne Observatory tours officially relaunch properly. I think it's the first, or not entirely sure. It's either the first or the second Monday in March. It may not be the first because that's the long weekend, or that's the week before the long weekend. So it might be of the long weekend, but tours are relaunching. The information, there's some information on the website. There's more coming from the gardens, and ticketing will be done through the gardens with the ASV hosting the tours. We're still not ready? I'm running out of things to pad with. Well, Bill's gonna talk to us about February sky. And I've noticed, Bill, that we've got a bit of an aurora happening on the projector screen behind us. Yeah. We've created our own aurora, which is interesting. You know, you have to wait till you turn the projector on. So what is in the sky? What are we going to be talking about? Just while I've got you.
Stars.
Stars. Yeah. Stars. Some galaxies. Some nebulas. What's the image of the month to image? What's the object of the month to image? Well, what have you been targeting recently?
Well, goodness gracious.
Everything.
Yeah, I've been trying to get some stuff going on the ASV's,
On our 2 meter.
the 2 meter scope
Yeah.
dome. Yeah.
Yeah.
Do you want me to grab?
No,
that?
you can have that now.
Okay. Thanks. Yeah.
All yours, Bill.
Thanks. Oh, look. Oh, there is an aurora. Oh, wow. Okay. I think if I just hit that button there, it should. Now, I've been going to need my glasses because I can't read my own screen. There we go. Slideshow. Start from first slide. It's a good place to start. Now, I've been experimenting with a jigger, but it doesn't work very well. So if it doesn't move forward when I say it should move forward, then I'll have to come back and sort of press buttons on the computer. Now, I don't know if I can be heard in this as against you. I think I have to speak loudly to be heard at the back, but quietly so that I don't destroy the microphone. So I could do that. All right. Okay, so this is the What's in the Sky area. Now I'm going to be talking about the late February to early the March, because that's more or less between this meeting and the next one. Oh yes, it's fine. Tonight we always start with acceptance that we're on the lands of the Bunurong and the Wurundjeri peoples of the Kulin Nation. So now I'm going to be talking largely about the general conditions for this time of year. And then I'm going to want to talk about something called the observing donut, which sounds interesting, but it's relevant to most people. I'll explain that. And then I'm going to get into the What's in the Sky thing. And as always, I'm going to talk about the moon, how you get orientated in terms of constellations, bright stars, and what planets there are left. And then I'll go through a set of targets that I'd be thinking about for tonight. Then the next section is the idiots who get up early in the morning before the sun rises, and they do a bit of observing then. And I'll finish off by saying what's the stars going to be looking like next month. Finish by some random stuff. So let's see. Yes, it's working. So the general conditions for for this time of year. First of all, happy Valentine's Day. I'm surprised no one said that before. Now it's late summer. It's getting towards the equinox, which means that the atmosphere around us is still very warm, and that means that observing is still not fantastic. I think it's easier to do observations, certainly through a telescope in the winter when it doesn't twinkle. Now, I'm not quite sure if everyone knows what twinkling is all about. It's has anybody been swimming in a river in summer, and it's nice and cool in summer, and suddenly this little bit of warm water goes past and you go, ooh. You sort of look at the people upstream and you think, hello. The atmosphere is kind of like the same sort of thing. There's warm and cold parts to it, and they sort of swirl around. And when light comes through, it's like a set of lenses, and it wobbles the light ray a little bit, which means that the star will be wobbling around a little bit, and sometimes going in and out of focus or moving left and right. If you look at the moon through a very large, a long focal length telescope on a summer's day, it looks pretty awful. It's just like blah, blah, all over the place. So that's what twinkling is, and it's most prevalent at around about late summer. So let's see, sunset. It's about 8:20 p.m. tonight. It's dark enough about an hour later. What time is it now? I have no idea. So it's going to be dark enough for us to look at some stars through the telescopes later on. In March, about this time of the month in March, we're going to have a lot less daylight. The sun sets at about 7:40, which that's typical of this time of year, because it's all sine waves. At the time of the equinox, we're losing or gaining, depending on which one you're talking about, more and more light, or the most light every night. Sunrise just after 6:45 a.m. It's too late for observation about an hour before. So go to bed, people. It's about 7:20 a.m. In 14th of March. So again, you're gaining light, gaining dark, losing light at quite a lot of rate. Young astronomers. I used to have a young astronomer. She's grown up a bit now. She's a middle-aged scientist. Early in term one may not be the best time for watching the stars. What you should do is try observing the moon during the afternoon at the first quarter, which is about the next couple of days. It's going to be up in the afternoon, or it's certainly towards the afternoon. It will kind of be in the east in the afternoon. And so what you do with your young astronomers is you give them a pair of binoculars and you tell them to look at whatever they like to see, but you put them in the shade of a building, because that way they can't see the sun. So you save your kids' eyes. It's probably nice for them to have eyes. Planet season is largely over. Jupiter is the only one which is still there. The only easy one still there that you can see with your naked eye and chase it down with a pair of binoculars. With any luck, we'll have a bit of a view of Jupiter tonight, but probably by this time next month, it's going to be probably too late too low to see. The other thing I was going to remind you of is the Messier Star Party in Hamilton. I don't think I really need to do that because Mark's already done it for me. So there you go. Thanks, Mark. Okay, who likes donuts? Yay! Now, when you're talking about telescopes, can you see easily to the horizon? Now, if you're in a city, or if you're in your own backyard, it's very hard to see all the way down to the horizon. My normal rule of thumb is around about 30 degrees, because you get trees, buildings, and there's atmosphere as well. You just can't see very well to the horizon. At the same time, can you see easily to the zenith? Now, I've got a long refractor, and it's on a fairly large mount, and I can actually see to the zenith. But a lot of long refractors, like an ED120, it's going to crash into the leg of the tripod, and even if it doesn't, you're going to be standing like this, trying to see to the zenith. So the zenith is hard to hit. Fork-mounted SCTs, if you've got a Schmidt-Cassegrain, particularly if you're trying to put a camera on it or something like that. When that goes straight to the horizon, often what's underneath the bottom of the telescope can crash into the bottom of the mount. This is a bad thing. So again, no zenith. If you've got a Dob, you're going to need a step ladder. Pardon? Huh, there you go. I'm a refractor guy. All right, you'd need a stepladder to get near it anyway. And some observatories, as I found out on Monday, don't open right to the very top. I was all prepared to see something which was really great, and I realised it was directly above us, and I disappointed everybody around me. So basically, the bottom line, the donut is best between 30 degrees and about 80 degrees of altitude above you. So when you're planning a night, think about the observing donut and yeah, have fun. Okay, moon. First quarter is on Saturday, which means that it's over this week. It's setting earlier in the evening. Lunar X, which is something I'm going to come back to hopefully every month. Not this month. The Lunar X is out of view. It's going to be. It happens when the moon is below the horizon. By late February, the end of this month, the moon is going to be getting fuller and fuller, and it's going to be higher in the sky after dusk, and it's going to be well north of the equator. Now, the moon's orbit is on quite a different plane to the sun's, well, the sun's apparent orbit. I'm not going to say that the sun rotates around the Earth. That would be controversial. But because of the difference in those orbital planes, every 2 weeks the moon goes from the north of the equator to the south of the equator. So yeah, it's going to be north of the equator, which means it's going to be fairly low from where we are at the moment. The full moon is on the 25th, and if you're interested in this sort of thing, it's a mini moon because it's like at its apogee or apotheosis. I don't know what they called it. By late February, it's going to be going below the equator again and coming and moving towards the first quarter, and that becomes a morning object. And on the 10th of March is the new moon, which is just in time for the Messier Star Party. So if anybody wants to observe the moon at the Messier Star Party, it's going to be a bit of a disappointment for you, I'm afraid, because it's going to be not round there. Right, now this is where I would really, really like to turn off the lights because we can't see very well there. Whoops, did I just... Oh, look at that. Boink. No. There we go. There we go. Now, okay, it's very romantic in here now, and probably the camera can't see me, which is, I got to say, a good thing. Okay, these things are, or these maps are what I described last month, and they're going to be sky at 10 p.m. facing south. So, getting orientated, always look for the Southern Cross. That's the first thing you're going to be looking at. Now, it's around about 9 o'clock from the South Celestial Pole. No, whoops. There's the South Celestial Pole there. And so it's around about 9 o'clock from there. Don't think about the zenith because that's wrong. You've got to find your South Celestial Pole, and it's about 9 o'clock from there. This thing's working. Now, Orion is the other thing that most people recognise. There he is up there, and he's always on the equator, but he's just past the meridian. There's a meridian there. So he's just past the meridian at about 10 o'clock, which means that your telescope is going to have to, well, you're going to have to flip your telescope over or at least have it east of the pier. Hyades and Pleiades, they're still there. They're getting fairly low, but the Pleiades is still there, just that little dot there. And there's Hyades, and that's Aldebaran, by the way, not Aldebaran. That's fine. Now the thing's not working. Oh, there you go. Right, okay, we've got some orientation stars coming up. I might have to do that. Okay, we've got Canopus and Sirius. Now they're straddling the zenith at about this time. So you'll be able to stand there and look straight up, and you're going to see Canopus and Zenith and Sirius. Obviously, Sirius is the brighter of the two, and it's sort of just not very far from Orion, so you should be able to figure out those two. Procyon and Achernar are on the opposite sides of that, so we're getting a bit of a line of stars. The really bright stars here. So there's Achernar down in the southwest, and Procyon up in the northeast. Okay, Castor and Pollux have just more or less come into view. They're up there. They're quite fun to look at. I only discovered the other day because Colin showed me that Castor is in fact a double star, and it's quite a nice little double star. And whoops, I've gone too far. See if we can get back one. Yeah, there we go. Now we are getting into Carina season. Carina is now above the 9 o'clock area. Carina is this sort of area, and there's a mess of stuff in there. And I'll get back to what's in that area shortly. But before I do, Jupiter is over there, and it is getting low, but it's obviously fine at the moment. if you're going to be doing any observation, it would be a good idea to start with Jupiter because it's going to set. Okay, so these are my targets for the evening. Now, I've been talking to a couple of people, and I've color-coded my my binoculars, small telescopes, large aperture telescope, and high magnification telescope to make it a little bit easier, hopefully, to understand what I'm talking about. Okay, obviously we're going to start with Jupiter. Jupiter is well, there, as I just said. You're going to need a high magnification telescope. Anyone can find it, and with a pair of binoculars you can see the moons, but if you want to see any detail on it, you're going to need to have relatively high magnification telescope. So Schmidt-Cassegrain or something like that. Now, M45, the Pleiades, is almost the opposite of Jupiter in terms of size and intensity. So you're going to need a pair of binoculars or small telescope is perfect for the Pleiades. If you put too much magnification on it, it just looks like a blob of stars. It's actually pretty boring if you have too much magnification. Sometimes magnification isn't your friend. But that's what it looks like. Now, I think that's Paul Litchen's photograph. I'm not quite sure. But Paul took a nice photograph of the Pleiades on Vic South, so I think that was it. Oh, no, it's not, because it's got, it's gone now, but that had diffraction spikes. He was using a refractor. Sorry, Paul. The next thing is there's a group of stuff inside Orion. Obviously, Sigma Orionis is a quad star system. It's actually, I was looking at it the other day. There's actually 7 stars there. I'm not quite sure if the 3 stars on the three like dim stars are actually interacting with the 4 stars in a line. I'm sure that Colin can tell me. No, he's shrugging his shoulders. Okay. So anyway, Sigma Orionis is a really good little thing to look at. You will need a fairly high magnification telescope to see them. Speaking of high magnification telescopes, I'm hopping over M42. I'll get back to that. The trapezium inside M42, you're going to need a lot of magnification for. You can see it with a small telescope, but it's not going to look like very much because that's a very, very tight little cluster. With a large magnification telescope, you can split it into 4, 5. Somebody said that they said 9. They've said 9. Around the trapezium, obviously, is M42. Which is the Great Nebula. You're going to need a lot of aperture to see this, and you're also going to need to be in a dark sky site. You can see it from Melbourne, even from here. It's much more impressive if you're members of the ASB. Come up to the LMDSS and look at it through the 40-inch telescope. It's amazing. While you're there, you've got to look at the Flame Nebula. People tend to They tend to discount the Flame Nebula. It's the boring cousin of the Horsehead, but it's kind of pretty. So keep a look out for the Flame Nebula as well. You're going to need to have a large aperture telescope. And there's Sigori. I pinched that off the internet. It's Wikipedia, so it's kind of asking for it. It's not the world's best photograph, but it's better than the one I've got. Obviously, there's oh geez, this screen is awful. Well, all right, it looks much better here. That's a hydrogen alpha photograph of M42, and there's the Horsehead, and obviously the Flame Nebula there, and that guy there is Alnitak, the star that every astrophotographer wants to extinguish. Click. Okay. The next thing I'd be looking at is, because it's not very far away, just hop over Sirius and you can find southern Albireo. Southern Albireo is about 5 degrees south, I think, of Sirius, or am I thinking of something else? Anyway, it doesn't matter. Look it up in your funkin' waggles. It's a double star, and it's really, really cool because there's one blue and one yellow one. So look out for that. It's quite a treat. Small telescope, again, you won't need a huge amount. It's a fairly comfortable double. But if you can get more magnification on it, then you'll be able to split it a little easier. Again, it's disappointing, but this is a photograph of southern Alberio. Hopefully you can see that there are two stars in there. There's a purple one and a sort of a greenish yellow one. Here it's actually blue and yellow, but it's up there it's slightly different colours. The interesting thing about this photograph is that it was taken, I took it myself, remotely from the LMDSS dome. And I did that entirely from my study at home, just need a computer, the right training, and a time slot. And this is something which is coming to ASV members really soon. So keep a lookout for that, because that's really cool. You can do your own armchair astrophotography. The next thing I'd be telling people to do is hop back over the meridian, and because there's P Eridani, which is the cat's eyes double, and Theta Eridani, which is Achernar, that's another double, and Zeta Reticuli. Now, I was talking about Zeta Reticuli the other day. It's the home of the grey aliens, so keep a lookout for them too. Zeta Reticuli is a very, very wide double. You can split it using a pair of binoculars and a small telescope. So it's actually quite fun. P Eridani is tighter, and Theta Eridani is, I believe, tighter again. So have a look at those. Now, before we get to Carina, there's the Tarantula Nebula. You're going to need to have some aperture, and you're going to need to be in a dark sky site. You can see it from Melbourne, but it's much more exciting out in the boonies. Right. Oh, and that's. Look, it's Narrowband. That's supposed to be the Tarantula Nebula. I'm trying to get images going. Finally, we get to the star of the show. It's Carina season. So I'm going to pick 5 things inside this area. It's the Triple Cross area. So I'm going to talk about the Diamond Cluster, the Southern Pleiades, the Pearl Cluster, the Gem Cluster, and the Blue Planetary Nebula. But to do so, I'm just going to zoom in a fraction. Now, here we have, down the bottom, we've got the real, genuine Southern Cross. Then there's the Diamond Cross up there, and then there's the False Cross. Now, when you're up at the dark sky site, you might lose those. There's so many stars in the foreground, or just around them, that it's kind of hard to find them. But yeah, you can use those as good little way stations. I don't know, signposts. And here are some photographs. Oh, dearie me, again, it's not fantastic. Now, these photographs are actually, they're taken by astrophotographers, idiots like me. Actually, I took this one here. Oh, no, I didn't. That's Wikipedia. Oh, one of those is mine. Doesn't matter. This one, the Southern Beehive, is actually closer to what you're going to see with your eye. So I suppose I'm standing in the way, aren't I? The Gem Cluster is really cool, but you probably won't see any of that nebulosity around it unless you've got a really wide aperture telescope. The other ones are probably a little bit deep, so you won't see the myriad of stars behind them. So you'll probably see something more like the Southern Beehive there. Now, I've marked on the map there where they all are. So I'll probably push ahead and not talk too much about that. The Blue Planetary Nebula is well, I saw it for the first time in my life last week. Thank you, Colin. Yeah, it's really, really cool. It's very, very small. So you'll need a chunk of magnification, but obviously aperture is king. So I mean, the 12-inch here, you might be able to see it. The 8-inch, probably not. I'm not entirely confident of getting that. So that was my night tour. Just quickly, going through the 5 a.m. stuff, facing south. Venus is starting to get lower. It's done its sweep, and it's going to go and hide behind the sun. Mars is just on the horizon. I don't think it's moving very fast at all. Mercury is gone. But 5 o'clock tomorrow is one of those times when you'll see Scorpius for the first time for the year. So keep an eye out for that. Scorpius to Sagittarius is my favourite. Well, one of my favourite parts. I think they're all my favourite. One of the favourite parts of the sky. M8 and M20 are in that little mess there, just in that little green dot there. You'll be able to get them with any luck in the same telescope image. You certainly can with a wide angle camera. And the dark doodad, which is this Mark was asking me about what's the challenge object. The dark doodad is definitely the challenge object this year or this month. So that's down below the Southern Cross, but it's fairly accessible at this time of year. So here is M8 and M20 in the same field. You'll probably need a special pair of glasses to see that. That's pretty awful. But if you're looking for a photograph of the dark doodad, you really can't go past the yearbook. So Eddie Pang's got his dark doodad on the front page of the yearbook, and if Eddie, you're out there in Cyberland, sorry what I've just done to your photograph. That's awful. So, all right. Next month, just quickly, the cross is going to be about 10 o'clock, not 9. It's up there. There's 10 o'clock from the South Celestial Pole. Orion and Gemini will be both well past the meridian now. Pleiades is gone, but Spica has shuffled onto the stage, so we'll be able to use that as an orientation star. And that was a very fast end. Final notes. At 5 a.m. on the 23rd of February, which is about a week, Mars and Venus are going to be banged together on the eastern horizon. It's going to be really, really difficult. Sunrise is at 7 a.m., but I would encourage you, if you've got a view of the eastern horizon, go and have a look at it. I have not. I'm on the western side of a hill, so I'd have to burrow through quite a lot of dirt. But yeah, they are going to be very, very close together. So you've got about a 2-hour window of opportunity to go and see there. On the 29th of February, besides Leap Day, Saturn goes behind the sun. It actually doesn't go behind the sun; it kind of goes above the sun, but it's in, what do they call it, superior opposition. And 9th of March, just reiterating, the Messier Star Party in Hamilton. So be there or be square. So there you go.
Thank you, Bill. We're blind now. Apologies for the projector. It's decided it wants to produce an aurora for us.
No, it's just gone blind.
What we might do is, if I can get your slide in a presentation form to upload to, because I can upload it to YouTube and to Facebook for people so they can see the actual photos as well. That would be good. And you didn't have my favourite in there. You didn't have running chicken with all the bok globules.
Yeah, I thought I might have put that. I might put that in, but I thought that it might be just a little bit on the
nose.
Well, I don't know. Yeah, something like that.
Yeah. Well, I might have to go for what was the one with the nebula around it?
The M45.
No. Yeah. No. Yeah. Well,
the gem cluster.
Yes, I'm going to go for that. I want to try that with the phone.
Yeah.
Can you give that a go?
Yeah, it's right next to
oh no.
Garcia Marquez. No, that's the
Garcia, Gabrielle Mistral Nebula.
That's the one.
Yes. Yes.
I knew it was white.
Which actually looks like a side-eye profile of her.
Yes.
It does. It's one of the few objects in the night sky that looks like what they say it looks like. Just want to thank everybody for coming tonight and everybody for watching on the stream. We're going to go and enjoy some supper now and go over and have a look at the observatory, roll the roof off, and open the library as well. I'm pointing to the people who are going to do these things. And we will see you next month, where hopefully, fingers crossed, we'll have Professor Jeff Cook from Swinburne University coming along to give a presentation. Once again, thank you everyone for coming along.